Hello everyone and welcome to our 10.3 notes. We're putting a lot of our circle theorems together in this set of notes. Some of these y'all have seen and then some of these you have not yet seen. And so these are going to be different theorems that have to do with chords and arcs and angles. And so the first one says within a circle or incongruent circles, congruent central angles have common arcs. So let's mark that out. Let's color code this. Congruent central angles. So let's go ahead and name these. What are these congruent central angles? I'm going to name them angle AOB. If angle AOB is congruent to angle DOC, then what do we know about those arcs? Those arcs are going to be congruent. So arc AB is going to be congruent to arc CD. So let's do that in colors. Arc AB is going to be congruent to arc DC. So congruent central angles give congruent arcs. So what is the converse of that? Well, it just says it backwards. If you know that those arcs are congruent, if arc AB is congruent to arc DC, what do you know about those central angles? Those central angles must also be congruent. So angle AOB should be congruent to angle DOC. So it says the same thing forwards and backwards. All right, what does our next theorem say? Our next theorem says within a circle or incongruent circles, congruent central angles. So again, if we know that there are congruent central angles, let's do that in colors. If we know that angle AOB is congruent to angle DOC, what else do we know? We know that those are going to also have congruent chords. Those are going to be congruent chords, meaning that the chord from A to B is going to be the same, or is going to be congruent to the as the chord from D to C. So let's color code that. So that means that the chord that exists, not the arc, but the chord that exists from A to B is going to be congruent to the chord that exists from D to C. So what is the converse of that? It just says the same thing, but in reverse. So if we know that those chords are congruent, what do we know about those central angles? If the chords are congruent, then the central angles are going to be congruent as well. So then we know that angle AOB is going to be congruent to angle DOC. If the central angles match, the chords match. If the chords match, the central angles match. I know that we've kind of demonstrated that with our hands before as well. Okay. All right. Now notice this next one says something very similar. Within a circle or incongruent circles, if you have congruent chords, those congruent chords are going to have common arcs. So congruent chords are going to have common arcs. So if you start by knowing that these chords are congruent, B to A and C to D. So if you know that chord BA is congruent to CD, you know what, let's name it the same way as before. If we know that chord AB, it means the same thing, but just for consistency. If A to B is congruent to D to C, then what do you know about the arcs that get intercepted? That means that those arcs are going to be congruent to each other. So let's write that out. We know that this arc is going to be the same as, or congruent to this arc. So we know that those arcs are going to be congruent. So we know that arc AB is going to be congruent to arc DB. Those would have the same measure. So what is the converse of that? It says the same thing, just in reverse. If we know that, if we start by knowing that those arcs are congruent, then what do we know about the chords? That means that the chords must also be congruent. And you can see the symmetry in these three theorems. If I were to fold this circle along these vertical lines of symmetry, those would fold exactly in half on top of each other. The arcs would fold on top of the arcs, the central angles would fold on top of the central angles, and the chords would fold on top of the chords. So it's easy to visualize these theorems. All right, what does our next theorem say? Within a circle or incongruent circles, chords that are equidistant from the center or centers are congruent to each other. So we've learned this one before. We said that if O to E, the perpendicular distance, so there's that right angle, the perpendicular distance from O to E is the same length as the perpendicular distance from O to F. So if we know that O to E is equal to E to F, then what do we know? We know that those chords are going to be congruent to each other. So we know that this chord in pink, A to B, is going to be the same length as the chord D to C. So we know that, how do they phrase it? Chords equidistant from the center or centers are going to be congruent to each other. So we're going to have congruent chords here. So A to B, that chord, is going to be congruent to D to C. So what is the converse of that? It just says the opposite. If we know that the chords are congruent, just like we've talked about before, if we know that those chords are congruent, what do we know about the perpendicular distance to the center? We know that those are also going to be, those lengths are going to be equal. So we know that O to E is going to be congruent to E to F. All right, a few more, and we have talked about these before as well. In a circle, if a diameter is perpendicular to the chord, so what's our diameter? Our diameter is A to B. If that is perpendicular to our chord, then it bisects the chord and its arc. So we know that if A to B is perpendicular, which it is, to C to D, we know that what that means is that it bisects the chord and the arc, meaning that the segment from C to E is going to be congruent to the segment from D to E. So that's listed right here. And as well as those arcs are going to be congruent. So A to C is going to be congruent to arc A to D. Okay. So if A to B was a diameter and those were perpendicular to that chord, then we knew two things. Not only did it cut the chord in half, it also cut the arc in half. Okay. The next one says in a circle, if a diameter bisects a chord, so if we know that AB is going to be a diameter, and we also know that it cuts the chord in half, meaning we know that C to E is going to be congruent to D to E. So 2 out of the 3 are true. That means that all 3 must be true. That means that A to B must be perpendicular to C to D. That must be a right angle. If this is a diameter and we know that it bisects it, it must intersect at a 90-degree angle. Okay, so if 2 out of the 3 are true, all 3 are true. Okay? All right, if we know that A to B is the perpendicular bisector, meaning it's crossing at 90 and it's cutting this chord C to D in half. If it's cutting it in half, what do we know? We know that this A to B contains the center of circle O, and thus it is going to be a diameter. Okay? In a circle, the perpendicular bisector of the chord contains the center and thus becomes the diameter. If the chord contains a diameter, it is going to be, if the chord contains a center, it is going to be a diameter. So what we're doing on the back is we're practicing these problems. All of these different theorems get tested with a few of these problems, and you're solving for X.